Tonight, we're going to talk about something that happened at the closest object to Earth in the universe that has physicists questioning everything they thought they knew about how stars actually work. In December 2024, using NASA's Parker Solar Probe, the most heat-resistant spacecraft humanity has ever built, they did what was once considered impossible. They touched the sun. Not just flew near it, not just observed it from a safe distance, but actually plunged into the outer atmosphere of our star, a region so hot and so violent that for most of human history we couldn't even imagine sending anything there. The probe came within 3.8 million miles of the solar surface, closer than any human-made object had ever been, traveling at speeds exceeding 430,000 miles per hour, fast enough to fly from New York to Tokyo in under a minute. This was supposed to be one of the greatest engineering achievements in human history. A spacecraft surviving inside the sun's atmosphere, sending back data from a place no machine should be able to exist. But then something impossible happened. The data started showing things that shouldn't be there, patterns that defied decades of solar physics, behaviors that contradicted our most fundamental models of how stars work. And by the end of tonight, you're going to understand why what Parker Solar Probe saw during those harrowing minutes in the solar corona might be one of the most important scientific discoveries of our time, and what it tells us about how little we actually know about the burning ball of plasma that gives us life. Before we get started, if you love exploring the mysteries of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with where this story actually begins, because it doesn't start in 2024. It starts in 1958 with a young physicist named Eugene Parker who proposed an idea so radical that established scientists laughed at him. Parker suggested that the sun wasn't just sitting there quietly burning hydrogen. He claimed it was constantly blowing a massive stream of charged particles out into space in every direction, a phenomenon he called the solar wind. The established astrophysics community of the time thought this was nonsense. Space, they argued, was essentially empty. The sun emitted light and heat, yes, but a continuous stream of matter flowing outward at supersonic speeds. That seemed absurd. Parker's paper was rejected by the first journal he submitted it to. The reviewers couldn't find any errors in his mathematics, but they refused to believe the conclusion. It was only through the intervention of Subrahmanyan Chandrasekhar, one of the most respected astrophysicists of the 20th century, that the paper was eventually published. Chandrasekhar didn't necessarily agree with Parker's conclusions, but he recognized the mathematics was sound and that the idea deserved serious consideration. Within a few years, Parker was vindicated. The Soviet Luna 1 spacecraft in 1959 and later NASA's Mariner 2 in 1962 directly measured the solar wind streaming past them as they traveled through space. Parker had been right. The sun was breathing out a constant stream of charged particles, plasma made of protons and electrons traveling at hundreds of miles per second. This solar wind shapes everything in our solar system. It carves out a bubble called the heliosphere that extends far beyond Pluto, protecting us from cosmic radiation. It creates the auroras when it interacts with Earth's magnetic field. It strips away the atmospheres of unprotected worlds like Mars, slowly eroding them over billions of years. But Parker's discovery raised more questions than it answered, and the biggest question of all has haunted solar physicists for nearly 7 decades. It's a problem so fundamental that it makes you question whether we understand stars at all. The sun's visible surface, the photosphere, the layer we see when we look up at our star, has a temperature of about 5,500 degrees Celsius, or roughly 10,000 degrees Fahrenheit. That's hot, certainly, but it makes sense. The sun generates energy through nuclear fusion in its core, where temperatures reach 15 million degrees Celsius. As that energy works its way outward through layer after layer of dense plasma, it gradually cools until it reaches the surface at 5,500 degrees and radiates into space as the sunlight we feel on our skin. Here's where physics breaks down. Above the photosphere, in the outer atmosphere called the corona, the temperature isn't 5,500 degrees. It's not even 10 times that. The solar corona, That wispy halo you can see during a total solar eclipse has a temperature of 1 to 3 million degrees Celsius. In some regions, it spikes even higher. This makes absolutely no sense according to everything we know about thermodynamics. Heat flows from hot to cold, not the other way around. If you put a pot of boiling water next to an open flame, the water doesn't suddenly become hotter than the flame. Energy flows from the hot flame into the cool water until they reach equilibrium. But on the Sun, the situation is reversed. We have a relatively cool surface at 5,500 degrees, and just above it, an atmosphere at over 1 million degrees. This is called the coronal heating problem, and it's been called one of the most important unsolved questions in all of physics. For decades, scientists have proposed theories. Some suggested that magnetic waves traveling outward from the surface deposit their energy in the corona, heating it. Others proposed that countless tiny explosions, called nanoflares, constantly bombard the upper atmosphere, maintaining its extreme temperature. Still others suggested complex interactions between magnetic field lines as they twist, tangle, and snap back into place, release enormous amounts of energy in the corona. The problem was, we couldn't test any of these theories properly because we couldn't get close enough to the sun to actually measure what was happening. Every telescope, every satellite, every spacecraft that had ever studied the sun did so from a safe distance, observing the light coming from the corona but never actually being inside it. It was like trying to understand a hurricane by studying photographs taken from satellites in space. You can see the structure, you can track the movement, but you can't feel the wind, measure the pressure, or sample the air. To truly understand the corona, we needed to go there. We needed to send a probe directly into the sun's atmosphere and let it sample the plasma, measure the magnetic fields, and report back what it found. For decades, this was considered impossible. The sun is the hottest, most violent object in our solar system. Anything we sent close to it would be vaporized almost instantly. Spacecraft are typically built of metal and electronics, things that melt at temperatures far below what exists in the solar corona. The very idea of building a probe that could survive inside the sun's atmosphere seemed like science fiction. But NASA engineers refused to accept that this was impossible. Throughout the 1990s and 2000s, they worked on the problem, developing new materials, new heat shields, new ways to protect electronics from extreme temperatures. The breakthrough came with the development of a remarkable material called carbon-carbon composite, a substance that gets stronger at high temperatures rather than weaker, and can withstand temperatures up to 1,400 degrees Celsius while remaining structurally sound. Engineers designed a heat shield made of this material, 4.5 inches thick and 8 feet across, that would face the sun continuously, protecting the delicate instruments behind it in a perpetual shadow. The mission was named in honor of Eugene Parker himself, the man who had first predicted the solar wind back in 1958. At the launch in August 2018, Parker, then 91 years old, watched as the rocket carrying his namesake spacecraft thundered into the sky. It was the first time NASA had ever named a mission after a living person, a testament to how much his work had transformed our understanding of the sun. Parker passed away in March 2022, but he lived long enough to see his probe begin its historic encounters with the star he had spent his life studying. The Parker Solar Probe was unlike any spacecraft ever built. Its trajectory took it on a series of elliptical orbits around the Sun, with each pass getting progressively closer. The probe uses gravity assists from Venus to gradually lower its orbit, swinging past our planetary neighbor 7 times throughout its mission to lose energy and dive deeper into the solar system. With each Venus flyby, Parker's closest approach to the Sun gets smaller, until eventually, during its final encounters, it would pass within 3.8 million miles of the solar surface, well inside the corona itself. To put that distance in perspective, the Earth is 93 million miles from the Sun. The previous record for closest approach to the Sun was held by the Helios 2 spacecraft, which came within 27 million miles back in 1976. Parker Solar Probe would shatter that record by a factor of 7, going closer than anyone had ever dreamed possible. At its closest approach, The spacecraft would be moving at 430,000 miles per hour, fast enough that it would briefly become the fastest object ever made by human hands. The first close encounter happened in November 2018, when Parker came within 15 million miles of the Sun. The data that came back was already extraordinary, showing solar wind behavior nobody had predicted. As the mission continued and the probe got closer with each orbit, the discoveries kept coming. But the encounter everyone had been waiting for, the one where Parker would make its closest approach yet and dive deepest into the corona, was scheduled for December 24, 2024, Christmas Eve. NASA engineers and solar physicists around the world held their breath as the spacecraft executed the most dangerous maneuver of its entire mission. The hours leading up to the December 24, 2024 perihelion were among the most tense in NASA's recent history. The Mission Control Center at the Johns Hopkins Applied Physics Laboratory in Maryland, where Parker Solar Probe is operated, fell into a kind of anxious silence. Engineers monitored their screens, watching data streams that would soon go dark. Because here's the thing about diving into the sun's atmosphere at over 400,000 miles per hour. You can't communicate with the spacecraft while it's doing it. The heat shield is pointed at the sun, which means the antennas are pointed away from Earth. For days at a time during each close encounter, Parker Solar Probe goes completely silent, alone in the most extreme environment any human-made object has ever experienced. This silence is excruciating for the mission team. They've spent years preparing the spacecraft, programming every possible response to every conceivable problem. But during the actual encounter, they can't help it. They can't make corrections. They can't respond to emergencies. They can only wait and hope that the engineering they put into the probe is enough to bring it through the inferno. The spacecraft is essentially on its own, executing pre-programmed instructions and relying on its autonomous systems to handle anything unexpected. Parker Solar Probe carries a suite of 4 scientific instrument packages, each designed to measure different aspects of the solar environment. The FILDS instrument measures electric and magnetic fields, the lifeblood of the solar atmosphere. SWAP, the solar wind electrons, alphas, and protons investigation, samples the actual particles streaming past the spacecraft, measuring their density, velocity, and temperature. S-Letter 298 is the integrated science investigation of the sun, detects high-energy particles that get accelerated to enormous speeds in the corona. And WISPR, the Wide Field Imager for Solar Probe, takes pictures of the solar wind and corona from inside, providing a perspective no human has ever seen before. All of these instruments were active during the December 24th encounter. As Parker plunged toward its closest approach, they were recording data at unprecedented rates, filling the spacecraft's memory with information that would later be transmitted back to Earth. The probe entered what scientists call the Ulfvén critical surface, an invisible boundary in the solar atmosphere where the solar wind transitions from being magnetically connected to the sun to becoming truly independent of it. Below this boundary, plasma can still flow back toward the sun along magnetic field lines. Above it, the solar wind has officially escaped, traveling outward through the solar system. Parker had crossed this boundary in previous encounters, but during the December 2024 perihelion, it would spend more time below it than ever before, deep in the magnetized inner corona. For 3 days, the spacecraft was silent. The mission team went home, tried to sleep, tried to enjoy Christmas with their families, all the while knowing that their spacecraft was either still functioning or had been vaporized somewhere in the solar atmosphere. On December 27th, the moment of truth arrived. According to the pre-programmed schedule, Parker Solar Probe should have begun transmitting a brief signal called a beacon tone, a simple radio pulse indicating that the spacecraft was alive and functional. If that tone arrived on schedule, it meant the probe had survived. If it didn't arrive, well, the consequences were too painful to contemplate. The signal came through. Right on time, at exactly the moment predicted, Parker Solar Probe's beacon reached Earth. The spacecraft had survived its closest encounter yet. There were celebrations in mission control, hugs, tears, applause. Engineers who had worked on the project for over a decade allowed themselves to feel the weight of what they had accomplished. But the real work was just beginning. The full data from the encounter wouldn't arrive for weeks. The spacecraft transmits its scientific measurements slowly during the safe portion of its orbit when it's farther from the Sun and can point its antenna at Earth. When the data finally started arriving in January and February 2025, the analysis began. Teams of solar physicists around the world started examining the measurements, comparing them to models, looking for patterns. And almost immediately, they noticed something strange, something that didn't fit any of the predictions, something that made them wonder if their fundamental understanding of how the sun works was completely wrong. The first puzzling observation came from the magnetic field measurements. The sun's magnetic field, which extends throughout the solar system and reaches Earth as the interplanetary magnetic field, should be relatively organized close to the sun. Models predicted smooth, radial magnetic field lines pointing outward from the solar surface, gradually becoming more turbulent as the solar wind expanded into the solar system. But Parker's measurements showed something completely different. The magnetic field near the sun wasn't smooth. It was chaotic, filled with strange kinks and reversals that defied explanation. These reversals, which scientists had begun calling switchbacks during earlier Parker encounters, were sudden, dramatic flips in the magnetic field direction. The field would be pointing outward from the sun, then suddenly reverse and point inward for a brief moment, then snap back to its original direction. These weren't subtle variations. They were sharp, abrupt changes that happened in fractions of a second. And during the December 2024 encounter, deeper in the corona than ever before, Parker found that these switchbacks weren't rare anomalies. They were everywhere. The entire region was filled with them. This was completely unexpected. Models had predicted that switchbacks should diminish as you got closer to the sun, as the magnetic field became more organized near its source. Instead, the opposite was true. The closer Parker got to the sun, the more switchbacks it encountered, and the more violent they became. This suggested that whatever was creating these magnetic disturbances was happening right at the solar surface, or just above it, not somewhere out in the solar wind, as previously thought. The implications were profound. If switchbacks originate at the sun's surface and propagate outward through the corona, they might be the missing piece of the coronal heating problem. The energy carried by these magnetic disturbances could be exactly what's needed to heat the corona to its extreme temperatures. When the magnetic field snaps and reconfigures in these violent switchbacks, it could release energy that gets deposited into the surrounding plasma, raising its temperature dramatically. This isn't just a theoretical possibility. The new data suggested it might actually be happening, but the switchbacks were just the beginning. As scientists dug deeper into the December 2024 data, they found more anomalies, more behaviors that contradicted established physics. The temperature measurements were particularly perplexing. Inside the corona, Parker measured plasma temperatures that varied dramatically over very short distances. In some regions, the plasma was the expected 1 to 2 million degrees. In other regions, just a few thousand miles away, temperatures spiked to nearly 3 million degrees. And in still other regions, temperatures dropped to relatively cool values of just a few 100,000 degrees, almost cold by coronal standards. This patchy temperature structure didn't match any existing model of the corona. Solar physicists had long assumed that the corona, while turbulent, was relatively uniform in temperature when averaged over large scales. The new data showed this assumption was wrong. The corona is a wildly inhomogeneous environment with vast variations in temperature, density, and composition over surprisingly small distances. It's less like a uniform atmosphere and more like a chaotic patchwork of hot and cold zones, dense regions and tenuous regions, all interleaved and constantly changing. Even more bizarre were the particle measurements. The IS Letter 298, his instrument, detected high-energy particles streaming through the corona at energies that shouldn't be possible. Some of these particles had energies in the millions of electron volts, far beyond what standard solar acceleration mechanisms could produce. These energetic particles are dangerous. They're the kind of radiation that can damage spacecraft electronics, harm astronauts, and even affect technology here on Earth during solar storms. Understanding where they come from and how they get accelerated to such extreme energies has been a major goal of solar physics for decades. The December 2024 data suggested that these energetic particles are being accelerated within the corona itself, not in larger flare events as previously thought. The mechanism seems to involve those magnetic switchbacks. When the magnetic field violently reconfigures in a switchback, it can accelerate nearby charged particles to enormous energies. It's similar to what happens in particle accelerators here on Earth, except this acceleration is happening naturally all over the Sun's atmosphere on an enormous scale. This has implications that extend far beyond the Sun itself. If we can understand how the Sun accelerates particles, we might understand similar processes happening throughout the universe. Cosmic rays, the ultra-high energy particles that bombard Earth from deep space, are accelerated by similar magnetic processes in other stars, supernovas, and exotic objects like neutron stars and black holes. The Sun is essentially a nearby laboratory where we can study these acceleration mechanisms up close. But perhaps the most shocking discovery from the December 2024 encounter involved something scientists hadn't even been looking for. While analyzing data from the FILDS instrument, researchers noticed a strange pattern in the radio emissions coming from the corona. Plasma in the solar atmosphere naturally emits radio waves, and these emissions can tell us a lot about the conditions in the corona. The radio signals Parker detected were unlike anything previously observed. They had peculiar oscillations, regular patterns that didn't match any known solar phenomenon. At first, some researchers wondered if there might be an instrument malfunction. The patterns were too regular, too organized to be natural. But when teams independently analyzed the data, they all found the same signals. They were real. They were coming from the Sun, and they were genuinely mysterious. Some scientists have proposed that these regular oscillations are evidence of previously unknown wave modes in the corona, complex magnetic disturbances that propagate through the plasma in patterns we hadn't predicted. Others suggest they might be related to the structure of magnetic flux tubes, organized bundles of magnetic field lines that thread through the solar atmosphere. A few researchers, controversial but worth mentioning, have proposed even more exotic explanations. Could these signals be evidence of some kind of resonance phenomenon, where the entire corona oscillates in coherent patterns we don't yet understand? Could they reveal connections between the magnetic structure of the Sun and processes happening deep in the solar interior, in regions we can't directly observe? The truth is, we don't know yet. The patterns are real, they're documented, and they're inexplicable with current physics. They're one of the most intriguing puzzles to come out of the Parker mission so far. The combination of these discoveries, the ubiquitous switchbacks, the patchy temperatures, the energetic particles, and the mysterious radio signals, was forcing solar physicists to confront an uncomfortable truth. Our models of the Sun were incomplete in ways we hadn't appreciated. The realization that came over the solar physics community in early 2025 was profound and unsettling. For decades, scientists had built increasingly sophisticated computer models of the Sun, simulating its interior, surface, and atmosphere with ever greater detail. These models could reproduce many observed phenomena. They could predict the general behavior of the solar wind, simulate sunspot cycles, and even forecast some aspects of space weather. But the data from Parker Solar Probe was revealing that these models, however sophisticated they appeared, were missing fundamental physics. The Sun was doing things our equations couldn't explain. This is the kind of moment in science that's both terrifying and exhilarating. Terrifying because it means established understanding is wrong in ways we don't fully appreciate. Exhilarating because it means there are major discoveries waiting to be made. Throughout the history of physics, moments like this have preceded revolutions in our understanding of nature. The discovery that the predictions of classical physics failed at very small scales led to the development of quantum mechanics. The realization that Newtonian gravity couldn't fully explain Mercury's orbit contributed to Einstein's theory of general relativity. Now, in solar physics, we might be standing at a similar threshold, where the failure of our current models is pointing toward new physics waiting to be discovered. To understand why these discoveries are so significant, we need to talk about what the sun actually is in physical terms. The sun is a ball of plasma, a state of matter so different from solid, liquid, or gas that it sometimes gets called the fourth state of matter. In plasma, atoms have been stripped of their electrons, leaving positively charged ions and negatively charged electrons moving freely. This charged soup behaves very differently from ordinary matter. It conducts electricity. It generates and responds to magnetic fields. It can carry currents that produce their own magnetic fields, which in turn affect the motion of the plasma, creating feedback loops of extraordinary complexity. The sun is, in essence, a vast electromagnetic machine. Its behavior is governed by the equations of magnetohydrodynamics, or MHD for short, which combine fluid dynamics with electromagnetic theory. These equations are notoriously difficult to solve. Even with the world's most powerful supercomputers, solar physicists have to make simplifying assumptions to make any progress at all. They have to choose which aspects of the physics to include and which to ignore, hoping that the most important effects are captured in their simplified models. For decades, the dominant assumption was that the sun's plasma could be treated as a single fluid with averaged properties. You could talk about its density, temperature, and velocity at each point, and the equations would tell you how these properties evolved over time. This approach worked reasonably well for many problems, but it ignored something important. Plasma isn't really a single fluid. It's a collection of distinct populations of particles, ions, and electrons with different masses, different velocities, and different temperatures. In many situations, treating them as a single fluid is a fine approximation. But in the sun's corona, where the plasma is hot, tenuous, and strongly magnetized, this assumption breaks down. Parker Solar Probe's direct measurements have shown that ions and electrons in the corona often have very different temperatures, sometimes differing by factors of 2 or 3. The particles aren't in thermal equilibrium with each other. This shouldn't be surprising in retrospect. In a plasma that's being constantly stirred by magnetic disturbances, accelerated by waves, and heated by various processes, why should different particle species behave identically? But this realization complicates the modeling enormously. You can't use simple single-fluid equations anymore. You need separate equations for different particle populations, each with their own temperature, velocity, and evolution. The complications don't stop there. The particles in the corona aren't just hot in the conventional sense. Their velocity distributions, the statistical descriptions of how their speeds are distributed, don't follow the standard bell curve shapes that classical thermodynamics predicts. Instead, they show strange distortions, extended tails of unusually fast particles, sharp peaks at particular energies, and other anomalies that suggest non-equilibrium processes are at work. The plasma is being continuously stirred, agitated, and energized in ways that prevent it from settling into the smooth, well-defined statistical states that simple models assume. All of this means the corona is a fundamentally different beast than we had understood. It's not a hot atmosphere in the classical sense. It's a complex, multi-component plasma far from equilibrium, with energy being constantly pumped into it by mechanisms we're only beginning to understand. The temperature, in the classical sense, isn't even a well-defined quantity in some regions because the particles aren't in thermal equilibrium. You can talk about the average kinetic energy of particles, but that's not the same as saying they have a single temperature. This has direct implications for the coronal heating problem. If the corona is being heated by countless small-scale events like nanoflares or by the dissipation of magnetic switchbacks, the heating won't produce a thermal equilibrium plasma. Instead, you'll get exactly the kind of non-equilibrium, multi-temperature, complex state that Parker is observing. The fact that the corona looks weird from a thermodynamic perspective isn't a mystery to be explained away. It's a direct consequence of how the corona is being heated. The strangeness is the explanation, but this raises a deeper question. What is the mechanism behind all this heating? The switchbacks Parker has observed are tantalizing because they're so violent and so common, but they're not the whole story. To understand the full picture, scientists need to trace these phenomena back to their source. Where do switchbacks come from? What creates them at the sun's surface or just above it? And how does the energy they carry get converted into heat? The leading theory now involves a process called magnetic reconnection. This is one of the most important phenomena in plasma physics, and it's at work throughout the universe in places ranging from the sun to galaxies to laboratory fusion experiments here on Earth. Magnetic reconnection happens when magnetic field lines, which normally don't cross each other, somehow break and reconfigure, releasing tremendous amounts of energy in the process. Think of two rubber bands stretched in opposite directions. Normally they remain separate, but if you could somehow snap them and let them reform with different connections, the elastic energy stored in their stretching would be released. Magnetic reconnection does something similar with magnetic field lines, releasing enormous amounts of stored magnetic energy as heat, kinetic energy, and radiation. Reconnection events happen throughout the sun's atmosphere, from the smallest scales to the largest. Major solar flares involve large-scale reconnection events that can release energy equivalent to billions of nuclear weapons in just minutes. But smaller reconnection events, perhaps countless tiny ones happening continuously across the entire solar surface, might be the dominant source of coronal heating. Each small event releases a tiny amount of energy, but if there are enough of them, the total can heat the corona to its observed temperatures. These small events would also create the switchbacks Parker is seeing. As magnetic field lines reconnect and reorganize, they create propagating disturbances that travel outward through the corona. The December 2024 data has provided strong evidence for this scenario. Parker observed direct signatures of magnetic reconnection happening near the sun, including changes in the magnetic field structure, consistent with reconnection events, accelerated particles emerging from reconnection sites, and turbulent plasma motions that suggest energy is being deposited locally. These observations support the idea that reconnection-driven heating is a major contributor to the corona's extreme temperatures, possibly the dominant contributor. But here's where it gets really interesting. Parker's data also suggests that the reconnection events happening in the corona aren't isolated incidents. They're connected to each other in complex ways, with one event triggering others in cascading patterns. Magnetic energy in one region propagates outward through waves and currents, creating conditions that allow new reconnection events to occur elsewhere. The corona isn't just a hot atmosphere being heated by discrete events. It's a dynamic, interconnected system where energy is constantly flowing, being stored in magnetic fields, and being released through reconnection in patterns that span enormous ranges of size and time. This systemic view of the corona is changing how scientists think about solar physics. Instead of focusing on individual phenomena like flares or solar wind streams, researchers are increasingly looking at how all these phenomena are connected through the underlying magnetic structure. The sun's magnetic field, generated deep in its interior by the dynamo effect, extends throughout the corona and out into the solar wind. This field creates a kind of cosmic web that connects different parts of the solar atmosphere, allowing disturbances in one region to influence others far away. The implications of this interconnected view extend beyond pure scientific understanding. Space weather, the conditions in space that can affect technology and human activities, is a direct consequence of these solar processes. Solar storms can damage satellites, disrupt radio communications, knock out power grids, and pose serious health risks to astronauts and even airline passengers on polar routes. As our society becomes increasingly dependent on space-based technology, understanding and predicting space weather becomes more important. Parker's observations are providing crucial data that will improve our ability to forecast solar storms and protect our infrastructure. There's also a more philosophical dimension to these discoveries. For most of human history, the sun has been an object of wonder, worship, and mystery. Ancient civilizations built monuments aligned with solar events. Religions placed the sun at the center of their cosmologies. Even in scientific times, the Sun has remained somewhat enigmatic, a vast and powerful object whose inner workings we could only infer from limited observations. Parker Solar Probe is changing that. For the first time, we're actually inside the Sun's atmosphere, sampling its plasma directly, measuring its magnetic field firsthand, watching its dynamics in real time. We're moving from seeing the Sun as an abstract object to understanding it as a complex, knowable physical system. This shift in our relationship with the Sun is profound. The Sun isn't just an unchanging ball of fire in the sky. It's a dynamic, evolving system with its own internal logic and behavior. By understanding it better, we understand ourselves better because we are products of the Sun. Every atom in our bodies heavier than hydrogen was forged in the heart of a star, then scattered through space when that star died. We are made of stardust, and the Sun is the closest example of the cosmic forges that created us. Studying it teaches us about our own cosmic origins. But the discoveries from Parker Solar Probe weren't done yet. As more data came in from subsequent encounters, scientists found even stranger phenomena, things that would push the boundaries of our understanding still further. And one observation in particular, made during a close approach in early 2025, would prove especially mind-bending. It involved measurements of something that, according to all conventional physics, shouldn't have been there at all. The data that puzzled scientists most came from Parker Solar Probe's encounter in March 2025, just a few months after the historic Christmas Eve perihelion. As the probe made another close pass through the corona, its instruments detected something that initially seemed impossible. Pockets of plasma that were moving in directions they shouldn't be moving. Streams of charged particles flowing not outward away from the Sun, as you'd expect for solar wind, but inward toward the Sun. Some of these inward flowing streams were small, just brief blips in the data. Others were larger, persisting for minutes at a time as the probe flew through them. This finding was deeply confusing because the solar wind is supposed to flow outward. That's the whole point of it. Energy and pressure deep in the solar atmosphere accelerate plasma to enormous speeds, sending it streaming away from the Sun in all directions. The idea that there could be significant amounts of plasma flowing back toward the Sun went against everything solar physicists thought they knew. It was like watching a river suddenly flow uphill. Something had to be wrong with the observations, or something had to be very wrong with our understanding of solar physics. The team investigated thoroughly. They checked the instruments for malfunctions, verified the data processing, ran independent analyses. Everything checked out. The inward flowing plasma was real. Whatever was happening, it was a genuine physical phenomenon, not an artifact of the measurement process. So what was causing it? The leading hypothesis involves the complex magnetic geometry of the corona. The Sun's magnetic field isn't a simple bar magnet shape. It's a tangled, ever-changing web of field lines, with some forming closed loops that arc from one part of the solar surface to another, and others extending outward into space as open field lines that become the interplanetary magnetic field. The closed loops, called coronal loops, can be enormous, sometimes stretching hundreds of thousands of miles above the solar surface. They're often visible during solar eclipses as the beautiful pink and red structures of the chromosphere extending into the corona. Plasma trapped on closed magnetic field lines doesn't escape into the solar wind. Instead, it can flow back and forth along the loops, sometimes ascending, sometimes descending. The inward flowing streams Parker detected might be plasma flowing down the legs of large coronal loops, returning to the solar surface after being lifted up by previous heating or pressure waves. This would explain why these flows exist alongside the outward flowing solar wind. They're not from open field regions, but from closed magnetic structures interleaved throughout the corona. But this explanation, while plausible, raises new questions. How does plasma get launched upward in the first place to then fall back down? What heats it? What causes the flow patterns to be so complex and variable? And how do these inward and outward flows interact with each other? The corona is starting to look less like a uniform atmosphere and more like a complex circulation system, with material flowing in multiple directions simultaneously, with hot and cool regions interleaved, with magnetic structures of all sizes and shapes constantly forming, evolving, and dissipating. It's an environment of staggering complexity, and we're only just beginning to map it. There's an even more startling aspect to these observations. Some of the inward flowing streams contained particles that were highly energetic, moving fast despite traveling toward the sun. This is genuinely strange, because particles accelerated by the sun should be moving away from it, carrying energy outward. Particles moving inward at high energies suggest that some acceleration mechanism is operating that doesn't simply blast particles away from the sun. Instead, it seems to be accelerating particles in various directions, including back toward the solar surface itself. One possibility is that magnetic reconnection events near the sun's surface can accelerate particles both outward and inward simultaneously. When magnetic field lines reconnect, they release energy that can launch particles in opposite directions along the new field lines. Some particles fly outward into space, contributing to the solar wind and the population of energetic particles in interplanetary space. Others fly inward, racing back toward the solar surface, where they ultimately deposit their energy when they collide with the denser plasma there. This bidirectional particle acceleration might be a key mechanism for transferring energy throughout the solar atmosphere, helping to heat both the corona and the underlying chromosphere and photosphere. These observations are forcing solar physicists to fundamentally rethink the relationship between the solar atmosphere and the solar wind. Traditionally, these have been studied as somewhat separate phenomena. The solar atmosphere was viewed as a relatively bounded region close to the sun, while the solar wind was the stream of particles flowing outward into the rest of the solar system. The boundary between them was the Ilfane critical surface I mentioned earlier, beyond which plasma was supposedly free to flow outward without being controlled by the sun's magnetic field. But Parker's data suggests this boundary is fuzzy, dynamic, and complex. Plasma can cross it in both directions. The solar atmosphere extends much further than previously appreciated, with magnetic structures and dynamic flows persisting far out into what was thought to be the realm of the solar wind. The wind itself isn't a smooth, uniform outflow, but a turbulent, structured medium with embedded fast and slow streams, density variations, and complex magnetic features. Understanding the solar wind requires understanding it as a continuation of the corona, not as a separate phenomenon. This new understanding has practical implications. Space weather forecasting, which we depend on to protect satellites, astronauts, and ground-based technology, has traditionally relied on simplified models of the solar wind. We track major solar events like flares and coronal mass ejections, then predict how their effects will reach Earth based on relatively basic propagation models. But if the solar wind is far more complex than we thought, with bidirectional flows, switchbacks, and other dynamic features, our forecasting models need to become more sophisticated. We need to capture the actual complexity of what's happening between the Sun and Earth, not just track the most obvious bulk features. NASA and other space agencies are already working on this. New generations of space, where the models are being developed that incorporate Parker's findings about the corona and solar wind. These models will allow more accurate forecasts of geomagnetic storms, radiation events, and other space weather phenomena that affect our technology. As humanity becomes more dependent on space-based infrastructure for communications, navigation, and other essential services, the value of accurate space weather forecasting only grows. But there's another aspect of the Parker data that's worth discussing in detail, because it relates to something even more fundamental than the corona's heating or the structure of the solar wind. It relates to how stars work in general, to the basic physics of stellar atmospheres throughout the universe. The Sun is just one star. There are hundreds of billions of stars in our galaxy alone, and trillions of galaxies in the observable universe. Every one of those stars has its own atmosphere, its own corona, its own version of stellar wind. The processes happening at the Sun aren't unique to it. They're happening at stars throughout the universe, on every scale from tiny red dwarfs to massive blue giants. By understanding what's happening at our Sun in unprecedented detail, we're learning about stellar physics in general. This is particularly important because stars are the fundamental building blocks of cosmic structure. They're where the heavy elements that make up planets and life are forged through nuclear fusion. They're the source of the radiation that influences planetary atmospheres and habitability. They're the engines that drive galaxy evolution. Understanding stars is essential to understanding everything from the origin of life to the fate of the universe. Parker's findings suggest that stellar atmospheres are much more complex than our traditional models indicated. The processes happening in the sun's corona, magnetic reconnection, switchbacks, bidirectional flows, energy cascades, are probably happening in similar forms in other stars. But other stars have different masses, different temperatures, different magnetic field strengths and configurations. The basic physics is the same, but the specific manifestations could be very different. Studying the sun in detail teaches us what to look for in other stars, what aspects of their behavior might be revealed by future observations. This is especially relevant for the search for habitable planets around other stars. A planet's habitability depends on more than just its distance from its star. The star's behavior, its variability, its eruptions, its stellar wind, all affect whether a planet can support life. Earth's relatively stable environment exists in part because the Sun is a relatively quiet star, with predictable cycles and manageable space weather. Planets around more active stars face much harsher environments. By understanding stellar atmospheres better, we can better assess which exoplanets might actually be habitable, not just which ones are in the right temperature range. There's even relevance for understanding more exotic objects. Neutron stars and black holes have their own forms of strong magnetic fields and accelerated particles. Some of the same physical processes happening in the solar corona, scaled up enormously, occur near these extreme objects. Parker's detailed measurements of solar processes provide a kind of laboratory for understanding similar but more extreme processes elsewhere in the universe. But let's return to the sun itself, because there's still more to discuss about what Parker found. We've talked about magnetic switchbacks, complex temperature structures, bidirectional flows, and energetic particles. There's another category of discovery that's been emerging from the data, one that might be the most exciting of all. It involves the seismology of the sun, the study of how the sun vibrates and what those vibrations tell us about its interior. You wouldn't expect Parker, which is studying the sun's outer atmosphere, to tell us much about the solar interior. After all, the corona is on the outside, and the interior is, well, inside. But it turns out the sun's interior leaves fingerprints in its atmosphere. Waves and oscillations generated deep in the sun propagate outward, eventually reaching the corona and influencing what's happening there. By detecting these signatures, Parker can probe processes happening in regions of the sun that we can't observe directly. The sun is constantly vibrating. Sound waves and other forms of oscillations ring through its interior, much like a giant bell. These vibrations are generated by the turbulent convection in the sun's outer layers, where hot plasma rises, cools, and sinks back down in a continuous cycle. The motions of this convection generate waves that propagate through the sun, bouncing around inside and creating standing wave patterns. By studying these patterns, in a field called heliosismology, scientists can map the sun's interior structure, just as seismologists on Earth use earthquakes to study our planet's interior. Heliosismology has revolutionized our understanding of the sun's interior. We've mapped how temperature, density, and composition vary with depth. We've measured the differential rotation, the fact that the sun rotates faster at its equator than at its poles. We've discovered flows of plasma deep inside the sun, vast circulation patterns that carry heat and magnetic field from one region to another. These discoveries have been made primarily through observations of how the sun's surface oscillates, with sophisticated instruments tracking the tiny up and down motions of different points on the solar disk. But Parker is opening a new chapter in heliosismology by detecting the signatures of solar oscillations in the corona itself. As waves propagate from the solar interior outward through the atmosphere, they leave imprints on the magnetic field and plasma motions that Parker measures. By analyzing these imprints, scientists can extract new information about the sun's interior that wasn't accessible before. The implications of detecting solar oscillations in the corona are profound. For the first time, we have a direct probe of how the sun's interior dynamics connect to its outer atmosphere. The connection between these two regions has been one of the great mysteries of solar physics. We know that energy generated by fusion in the sun's core eventually emerges in the atmosphere, but the specific pathways by which it gets there and how those pathways influence atmospheric behavior have been hard to determine. Parker's measurements are providing the data needed to trace these connections in detail. One particularly intriguing finding involves the detection of certain wave types in the corona that scientists had predicted but never directly observed. These are called Ulfvén waves, named after the Swedish physicist Hans Ulfvén, who first described them in the 1940s. Ulfvén waves are oscillations in magnetic field lines, like waves traveling along a stretched string. But in this case, the string is a magnetic field line, and the medium it's traveling through is plasma. These waves can carry enormous amounts of energy, potentially enough to heat the corona to its observed temperatures. They've long been suspected as a key player in coronal heating, but actually detecting them, measuring their properties, and understanding how their energy gets converted to heat has been extremely challenging. Parker's instruments have now directly detected Ulfvén waves propagating outward through the corona, traveling along magnetic field lines, carrying energy from the solar surface up into the atmosphere. The measurements show these waves have the right properties, the right energies, and the right frequencies to be major contributors to coronal heating. As they propagate outward, they interact with the plasma in complex ways, gradually depositing their energy through various dissipation mechanisms. Some of this dissipation involves the magnetic reconnection and switchbacks we discussed earlier. Other dissipation happens through more subtle wave-particle interactions, where the oscillating magnetic field transfers energy to nearby charged particles. The picture that's emerging is one of remarkable complexity. The corona isn't being heated by any single mechanism. Instead, multiple processes are working together, with Ulfvén waves, magnetic reconnection, switchbacks, and other phenomena all contributing to the energy balance. Different mechanisms might dominate in different regions or at different times. The corona is a fundamentally multi-process environment, and understanding it requires understanding how these various processes interact and contribute to the overall energy budget. This multi-process view has implications for solving the coronal heating problem in a definitive way. For decades, scientists have searched for the single mechanism responsible for coronal heating, hoping to find one process that could explain everything. Parker's data suggests this search may have been misguided. There isn't a single mechanism. There's a complex interplay of multiple mechanisms, each contributing to the total heating in ways that depend on local conditions, magnetic field structure, and dynamic state. Solving the coronal heating problem doesn't mean identifying one process. It means understanding the full ecosystem of processes and how they balance each other. This kind of complexity is actually common in physics. Many seemingly simple phenomena turn out, on closer inspection, to involve multiple interacting processes. The behavior of fluids, the dynamics of weather, the evolution of ecosystems, all involve complex interactions between many different mechanisms operating on different scales. Solar physics is just another example of this general truth. Nature rarely allows itself to be reduced to single, simple explanations. Real understanding requires grappling with the full complexity of natural systems. But there's a deeper implication that goes beyond solar physics. The way Parker is revealing the complexity of the sun's corona mirrors a broader trend in modern physics. As our measurement capabilities improve, as we can observe natural systems in more detail than ever before, we keep finding that things are more complex than we thought. Simple models that worked well at low resolution often fail when examined more closely. New physics emerges from the cracks in old theories. This isn't a sign that science is failing. It's a sign that science is succeeding, that we're uncovering deeper layers of reality that were hidden before. The sun is teaching us this lesson in a particularly dramatic way because it's so close, so accessible to direct study, and yet still revealing surprises after centuries of observation. If we can be wrong about the sun in such fundamental ways, what other apparent certainties might we be wrong about? This kind of humility, the recognition that our current understanding is provisional and incomplete, is at the heart of the scientific enterprise. It's what drives scientists to keep questioning, keep observing, keep building better instruments and theories. Parker Solar Probe represents the cutting edge of this scientific enterprise. The spacecraft itself is a marvel of engineering, a testament to what humans can accomplish when we set our minds to seemingly impossible tasks. Let's talk about the engineering for a moment, because it deserves more attention than it typically receives. Building a spacecraft that can survive inside the sun's atmosphere was once considered impossible. The challenges seemed insurmountable. How do you protect electronics from temperatures that can reach thousands of degrees? How do you keep instruments cool enough to function while their surroundings are baking? How do you maintain communication with Earth from inside an environment that interferes with radio signals? The solutions developed by NASA engineers and their partners are nothing short of extraordinary. The heat shield, called the Thermal Protection System, or TPS, is at the heart of the design. This 4.5-inch thick disk of carbon-carbon composite faces the sun continuously during close approaches, absorbing the intense solar radiation and protecting everything behind it. The shield gets incredibly hot, reaching temperatures of about 2,500 degrees Fahrenheit at perihelion. But behind it, in the shadow it creates, temperatures stay close to room temperature, allowing the spacecraft's instruments and electronics to function normally. This isn't simple shadow protection like you get holding a beach umbrella. The sun's radiation comes at the spacecraft from a wide range of angles as the probe rotates and moves through the corona. Maintaining the heat shield's orientation requires extraordinarily precise spacecraft attitude control. The probe uses small reaction wheels and thrusters to keep itself oriented properly, with the heat shield always between it and the sun. Even small deviations in orientation could expose vulnerable components to direct sunlight, potentially destroying them in seconds. The instruments themselves had to be designed with their own thermal protections. Some sensors peek out from the edge of the heat shield, exposed to direct solar radiation, and they're made from materials that can withstand the intense conditions. The FIELDS antennas, for example, are designed to operate at thousands of degrees while still making accurate measurements of electric and magnetic fields. The solar cells that power the spacecraft are made from advanced materials that can handle the high temperatures and intense radiation of the inner solar system. Communication is another challenge that required innovative solutions. Standard radio communication from a spacecraft to Earth requires pointing the antenna at our planet, but during close solar approaches, the heat shield is pointing at the sun, which means the antenna is pointing away from Earth. So Parker can't communicate during these critical periods. Instead, it stores all its scientific data in onboard memory, then transmits it back to Earth during the longer portions of its orbit when it's farther from the sun and can safely orient its antenna toward home. The trajectory of the mission is itself a feat of engineering. Getting close to the sun is harder than it sounds. You can't just point a spacecraft at the sun and fire its rockets. The Earth and other planets are moving rapidly in their orbits, carrying with them all the angular momentum of the solar system's formation. To get close to the sun, you need to shed that angular momentum, which requires either huge amounts of fuel or clever use of gravity assists. Parker uses 7 Venus flybys to progressively lower its orbit, each gravitational encounter with Venus stealing a bit of the spacecraft's energy and allowing it to dive deeper into the sun's gravitational well. This trajectory took years to design and required incredible precision in execution. The mission is scheduled to continue making close passes to the sun through 2025 and beyond. Each pass provides new data, new opportunities to test theories, and discover new phenomena. The cumulative knowledge from all these encounters will reshape our understanding of the Sun for generations to come. Even after Parker's primary mission ends, the data it has collected will be analyzed for decades, with new insights emerging long after the spacecraft itself has gone silent. There's something poignant about Parker's mission, too. The spacecraft will eventually run out of fuel and lose the ability to maintain its orientation. When that happens, the heat shield will no longer protect the rest of the spacecraft, and Parker will be destroyed by the same sun it has spent its life studying. The probe will become one with the star it was sent to investigate. There's a strange kind of beauty in this fate. After billions of miles of travel, after countless close encounters with the sun, Parker will ultimately merge with the object of its study. Its atoms will become part of the solar atmosphere, swept up in the very plasma it once measured. But for now, Parker continues to operate, continues to make discoveries, continues to challenge our understanding of stars. And the discoveries don't end with what we've discussed so far. There are aspects of the data that scientists are still trying to interpret, observations that don't fit any current theoretical framework, mysteries that may take years or decades to fully understand. Some of these involve such subtle effects that researchers are still arguing about whether they're real signals or instrumental artifacts. Others are clearly real, but completely unexpected, demanding new theoretical work to explain them. One example involves the discovery of what appear to be sustained density structures in the corona that persist for surprisingly long times. Most coronal features are turbulent and dynamic, changing rapidly as plasma flows and magnetic fields evolve. But Parker has detected certain density patterns that remain stable for hours or even days, much longer than turbulence should allow. These persistent structures suggest there might be organizing principles at work in the corona that we don't yet understand. Something is allowing certain patterns to maintain themselves against the chaotic forces that would normally destroy them. What could create such persistent structures? Some scientists have proposed that they might be related to the magnetic field topology, with certain field line configurations creating stable channels that confine plasma. Others suggest they might involve resonant interactions between different wave modes, creating standing patterns that persist because they're driven by external forcing. Still others wonder if there might be entirely new physics involved, some kind of self-organization that allows complex structures to emerge spontaneously from the chaotic medium of the corona. This last possibility is particularly intriguing because self-organization is a phenomenon that appears throughout nature in many different forms. Living cells, weather patterns, galaxies, all involve self-organization in various ways. Complex structures emerge spontaneously from simpler components, often in ways that seem to defy easy explanation. If the sun's corona exhibits its own form of self-organization, it would connect solar physics to broader questions in physics and biology about how order emerges from chaos. The question of self-organization in the corona connects to one of the deepest mysteries in physics. How does order emerge from disorder? How do complex patterns arise spontaneously in systems that should, according to basic thermodynamic principles, tend toward maximum disorder? The second law of thermodynamics tells us that entropy, a measure of disorder, tends to increase in closed systems. Yet we see order emerging everywhere in nature, from snowflakes to galaxies to living organisms. Understanding how this happens requires going beyond simple thermodynamics into the realm of non-equilibrium physics, where systems can maintain ordered structures by continuously taking in energy from their surroundings. The sun is a perfect example of such a system. It's continuously generating energy through nuclear fusion in its core, and that energy flows outward through its various layers before escaping into space. This continuous energy flow keeps the sun far from thermodynamic equilibrium, and that non-equilibrium state allows complex structures to form and persist. The granulation patterns on the sun's visible surface, where you can see countless cell-like structures rising and falling, are examples of self-organization driven by convection. The sunspot cycles, where magnetic activity waxes and wanes over roughly 11 years, are another example of self-organization, this time driven by the interaction between the sun's rotation, its convective flows, and its magnetic field. If similar self-organization is happening in the corona, it would represent a higher level of complexity than anything we've previously identified there. The corona is far more tenuous than the underlying layers of the Sun, with much lower density and pressure. Yet it maintains its enormous temperature and complex structure through processes that we're still trying to understand. The persistent density patterns Parker has detected might be windows into how this self-organization works at the largest scales. Solving these puzzles will require not just more observations, but also major advances in theory and computation. Current models of the solar corona, even running on the world's most powerful supercomputers, can't capture all the physics that Parker is revealing. They simplify too much, ignore too many small-scale processes, and miss the complex feedback loops that seem to govern coronal behavior. Building better models will require more detailed observations to guide the development, new theoretical frameworks that can handle the complexity, and ever-increasing computational power to run the simulations. This is where the broader scientific community comes in. Parker Solar Probe is just one instrument, providing one perspective on the Sun. To make sense of its data, scientists need to combine it with observations from other spacecraft and ground-based telescopes. The Solar Orbiter, a joint mission between NASA and the European Space Agency launched in 2020, is observing the Sun from different vantage points than Parker, providing complementary data on the solar atmosphere and out into the heliosphere. The Daniel K. Inouye Solar Telescope in Hawaii, completed in 2020, is the most powerful solar telescope ever built, providing images of the solar surface with unprecedented resolution. Combined, these instruments are giving us a multi-dimensional view of the Sun that wasn't possible before. International collaboration has been essential to making sense of Parker's findings. Solar physicists from dozens of countries have been working together to interpret the data, share insights, and develop new models. This kind of collaboration is one of the great strengths of modern science. No single team, no matter how brilliant, could tackle problems of this scale alone. By pooling expertise from around the world, we can make progress on questions that would be intractable for any individual or institution working in isolation. The progress being made is real, though sometimes slow and incremental. Each new paper published, each new conference presentation, each new theoretical development adds another piece to the puzzle. Gradually, the picture is becoming clearer. We're learning how the Sun's magnetic field evolves over time, how different layers of its atmosphere interact, how energy flows from the core to the corona and out into the solar wind. The fundamental questions are starting to find their answers, even if those answers are turning out to be more complex than we initially expected. Let me share another particularly striking discovery from Parker's mission. During one of its close approaches, the spacecraft entered a region where the solar wind was flowing at speeds significantly slower than expected, but with much higher density than normal. This slow, dense wind was interleaved with faster, more diffuse streams in patterns that resembled a kind of cosmic plumbing system. Different streams of plasma were flowing at different speeds, occupying different magnetic flux tubes, and being driven by different sources at the solar surface. The corona, instead of being a uniform outflow, was revealed to be a vast and intricate network of distinct streams, each with its own properties and origins. Tracing these streams back to their sources at the solar surface has been a major focus of research. Using a combination of Parker's in situ measurements and remote observations from other spacecraft, scientists have been able to identify the specific regions of the Sun where different solar wind streams originate. The fast wind, which moves at 500 to 800 kilometers per second, comes primarily from coronal holes, dark regions of the corona where the magnetic field opens up into space, allowing plasma to escape easily. The slow wind, which moves at 300 to 400 kilometers per second, has more diverse origins, coming from regions near the boundaries of coronal holes, from streamer belts where magnetic loops extend high into the corona before opening up, and from other complex magnetic features. This mapping of solar wind origins might sound like a technical detail, but it's actually crucial for understanding how the Sun connects to the rest of the solar system. The properties of the solar wind that reaches Earth, its speed, density, magnetic field, and composition, depend directly on where it originated at the sun. Different source regions produce wind with different characteristics, which in turn cause different effects when they interact with Earth's magnetic field. Understanding the connection between solar surface features and the wind reaching Earth allows us to predict space weather more accurately and prepare for its impacts. There's also significance for understanding the long-term evolution of planets in our solar system. The solar wind, over billions of years, gradually erodes planetary atmospheres. Mars, for example, lost most of its atmosphere over billions of years due to interactions with the solar wind. Venus has had its atmosphere transformed in complex ways. Earth's atmosphere has been protected by our magnetic field, but even with this protection, some atmospheric loss occurs. By understanding the solar wind in greater detail, we can better understand how planets evolve over time and what conditions make some planets habitable while others become barren. The relevance for exoplanet science is significant. Many of the most exciting exoplanet candidates are rocky worlds orbiting red dwarf stars, which are much smaller and cooler than the Sun. Red dwarfs have very different stellar winds, often much more violent than the Sun's, and the planets in their habitable zones orbit much closer to their stars than Earth does to the Sun. This means these planets are exposed to much stronger stellar winds, which can strip their atmospheres and potentially make them uninhabitable. By understanding solar wind processes in detail using Parker's data, scientists can better model what happens at red dwarfs and assess the habitability of planets around them. Beyond Earth's solar system, the same physical processes Parker is studying are happening at every star in the universe. Every star has a corona, every star has stellar wind, every star has magnetic activity that affects its atmosphere and surroundings. The specific manifestations differ from star to star, but the underlying physics is universal. Parker's discoveries are revealing aspects of stellar physics that apply throughout the cosmos. Future telescopes that observe other stars in greater detail will be able to use this knowledge to interpret their observations, recognizing in distant stars phenomena that Parker has revealed in our Sun. Let me touch on something that might seem speculative, but is grounded in real physics. Some of the patterns Parker has detected in the corona, particularly the complex magnetic structures and turbulent dynamics, share mathematical similarities with phenomena studied in completely different contexts. Plasma turbulence in the corona obeys similar equations to turbulence in fusion reactors here on Earth. Magnetic reconnection in solar flares involves the same physics as reconnection in laboratory plasma experiments and in the magnetospheres of other planets. The acceleration of particles in coronal switchbacks shares aspects with cosmic ray acceleration in supernova remnants. Even the self-organization processes we've been discussing have parallels in fields as diverse as cellular biology and complex chemistry. This unity of physics is one of the most remarkable features of nature. The same fundamental processes operate across an enormous range of scales and contexts. Studying the sun teaches us about plasma physics in general, and that knowledge applies everywhere plasma exists, which is most of the visible universe. By the way, plasma is by far the most common state of matter in the universe. Stars are plasma. The interstellar medium is plasma. The intergalactic medium is plasma. Even the universe right after the Big Bang was plasma. Solid, liquid, and gas, the states of matter we're most familiar with from everyday life, are actually relatively rare in the cosmos overall. Understanding plasma is essential to understanding the universe at its most fundamental level. This is why Parker Solar Probe is so valuable beyond just solar physics. The spacecraft is providing us with our most detailed look at plasma behavior in extreme conditions. Every measurement contributes to our broader understanding of how plasma works, which feeds into research on everything from fusion energy to astrophysics to space weather forecasting. The Sun is humanity's nearest plasma laboratory, and Parker is letting us study it from the inside in ways that weren't possible before. There's also a deeper philosophical dimension to all this work. By exploring the Sun in such detail, we're really exploring fundamental questions about how the universe works. What is energy, and how does it flow through complex systems? How do simple physical laws give rise to the staggering complexity we observe in nature? What is the relationship between order and chaos, between structure and turbulence? These questions go to the heart of physics itself. The answers we're finding at the sun apply far beyond it, helping us understand the universe at scales ranging from subatomic particles to entire galaxies. There's something both humbling and inspiring about this work. Humbling because it reveals how much we still don't know, even about the most familiar object in the sky. Inspiring because it shows what humans can accomplish when we apply our collective intelligence and creativity to genuinely difficult problems. The sun has been observed by humans since prehistoric times. Civilizations have built monuments to track its motion, religions have placed it at the center of their cosmologies, scientists have studied it for centuries. And yet, only now, with Parker Solar Probe, are we beginning to truly understand what's happening in its outer atmosphere. The fact that we can do this, that we can build a spacecraft capable of surviving inside the sun, that we can extract meaningful scientific data from such an extreme environment, is a testament to human ingenuity and persistence. The implications of Parker Solar Probe's discoveries extend into territory that some might consider speculative, but these areas are where the most exciting future research will likely focus. Consider what happens when we apply Parker's findings to the question of stellar evolution. Stars don't just exist statically. They evolve over their lifetimes, changing their structure, their luminosity, their magnetic activity. The Sun itself has been evolving since its formation roughly 4.6 billion years ago, and it will continue to evolve for billions more years until it eventually expands into a red giant, then sheds its outer layers, and finally becomes a white dwarf. The processes Parker is studying in the corona today have direct relevance for understanding this evolution. The Sun's magnetic activity, which drives much of what happens in the corona, has changed over time. Young stars are much more magnetically active than older stars, with stronger flares, more violent stellar winds, and more energetic radiation output. The Sun was significantly more active in its youth, and life on Earth had to develop in this more turbulent environment. Understanding how stellar atmospheres behave under different conditions, from young and active to old and quiet, helps us trace the history of habitability in our solar system and beyond. The Sun's magnetic activity follows roughly an 11-year cycle, with sunspot numbers waxing and waning over this period. We are currently in solar cycle 25, which began in late 2019 and is expected to peak around 2025. Parker Solar Probe has been making its close approaches during this active period, capturing data on how the corona behaves during the most dynamic part of the cycle. As the mission continues into the declining phase of cycle 25 and eventually into the rising phase of cycle 26, it will accumulate data on how the corona changes as the underlying magnetic activity changes. This temporal coverage is invaluable for understanding the relationship between the Sun's deeper magnetic dynamo and its atmospheric behavior. One observation from Parker that has particularly excited scientists involves the magnetic switchbacks we discussed earlier. As the mission has progressed and the probe has gotten closer to the Sun, scientists have noticed that switchback patterns are changing in ways that correlate with the solar cycle. During more active periods, switchbacks become more violent and more frequent. During quieter periods, they're less intense. This correlation suggests that the underlying physics generating switchbacks is connected to the broader magnetic activity of the Sun, providing another link between the corona and the deeper layers below. Tracing this connection further has led to some genuinely surprising hypotheses. Some researchers have proposed that the magnetic structures producing switchbacks are also responsible for the famous coronal mass ejections that periodically erupt from the Sun. Coronal mass ejections, or CMEs, are massive eruptions of plasma and magnetic field from the solar corona, sending billions of tons of material hurtling through space at speeds up to several million miles per hour. When CMEs are aimed at Earth, they can cause major geomagnetic storms with significant impacts on technology and infrastructure. Understanding how they form and predicting when they'll occur has been a major goal of space weather research. Parker's data suggests that the small-scale magnetic reconnection events producing switchbacks might be precursors to the larger reconnection events that drive CMEs. If true, this would mean we could potentially use switchback patterns to predict CME activity, providing earlier warning of dangerous space weather. The connection is still being studied, and definitive conclusions will require more data, but the implications are exciting. Better space weather forecasting could save billions of dollars by protecting satellites and power infrastructure, and could potentially save lives by allowing astronauts to seek shelter during dangerous radiation events. There's another aspect of Parker's discoveries that deserves attention, and it relates to something Eugene Parker himself proposed back in the 1980s. Parker hypothesized that the corona might be heated by a vast number of tiny eruptions, far too small to be individually detected from Earth, but collectively powerful enough to maintain the corona's extreme temperatures. He called these hypothetical events nanoflares, because each one would release perhaps a billionth of the energy of a major solar flare. The nanoflare hypothesis has been debated for decades, with some evidence supporting it and other evidence remaining ambiguous. The data from Parker Solar Probe is now providing direct support for the nanoflare idea, while also showing it's more complex than originally proposed. The spacecraft has detected countless small-scale events in the corona, brief flashes of activity, momentary disruptions in the magnetic field, sudden bursts of accelerated particles. These events are individually small, but they happen everywhere, all the time, across the entire corona. Their cumulative effect on the corona's energy balance is enormous. If you add up all the energy being released by these small events, it could easily account for the coronal heating that's been puzzling physicists for so long. The mechanism producing these events isn't entirely clear, but it likely involves the kind of magnetic reconnection we've been discussing. As the sun's magnetic field gets twisted and tangled by the continuous churning of plasma in the solar interior, energy gets stored in the magnetic field configuration. This stored energy eventually gets released when the field reconnects, snapping into a lower energy configuration. The release happens in countless small events scattered across the entire solar atmosphere, each one contributing a tiny bit of heating. The cumulative effect produces the multi-million degree corona we observe. If this picture is correct, it would resolve one of the longest-standing mysteries in solar physics. The coronal heating problem, which has puzzled scientists for nearly a century, would have its solution. But the resolution isn't a single elegant mechanism. It's a complex ecosystem of small events, all driven by the underlying magnetic dynamics of the sun. This is actually more interesting in some ways than a single mechanism would be, because it connects coronal heating to broader questions about how complex systems behave. These small reconnection events in the corona share interesting parallels with phenomena in other complex systems. Earthquakes on Earth are produced by similar mechanisms, with stress building up in fault lines and being released in events of various sizes. The distribution of earthquake sizes follows specific statistical patterns, with many small events and progressively fewer large events. Parker's data suggests the corona behaves similarly, with countless small events and fewer large flares. This statistical similarity hints at common underlying physics, perhaps related to self-organized criticality, a concept developed in the 1980s to explain how complex systems naturally organize themselves into states that produce events of all sizes in characteristic patterns. Self-organized criticality, if it applies to the corona, would have profound implications. It would mean that the sun's atmosphere is naturally maintained in a state poised on the edge of stability, where small perturbations can trigger events of any size from tiny to enormous. This kind of state, sometimes called the edge of chaos, is associated with maximum complexity and information processing. Living systems, including brains, are thought to operate near such critical states. If the corona operates similarly, it would connect solar physics to deep questions in physics, biology, and information theory. The connection between Parker's findings and broader scientific questions extends in many directions. Consider the role of solar activity in climate. The sun's energy output isn't perfectly constant. It varies slightly with the solar cycle and on longer timescales related to changes in solar magnetic activity. These variations are small, much smaller than the changes humans are causing through greenhouse gas emissions, but they're real and they do affect Earth's climate. Understanding the sun's variability in detail helps climate scientists separate natural solar influences from human-caused changes, which is essential for accurate climate science. Parker Solar Probe is contributing to this effort by providing detailed measurements of the processes that drive solar variability. By understanding how the corona changes over the solar cycle, how stellar winds vary in intensity and composition, how energetic particle events fluctuate, we can build better models of how the sun affects Earth's climate over short and long timescales. This information feeds into climate models that help us understand both past climate changes and project future ones. The connection between solar physics and climate isn't just academic. As humanity faces the challenges of climate change, accurate climate models become increasingly important. Decisions about energy policy, infrastructure planning, and adaptation strategies depend on our ability to project future climate accurately. Improvements in understanding the sun's role in climate, even when those improvements are modest, contribute to better climate models and better decision-making. There's also the deeper question of whether Earth-like planets around other stars can support life. The answer depends critically on the behavior of those stars, particularly their magnetic activity, their stellar winds, their flare frequency. The processes Parker is observing at our sun are happening, in different forms, at other stars throughout the galaxy. By understanding these processes in detail, we can better assess which exoplanets are likely to be habitable. Some of the most interesting exoplanet discoveries in recent years have been around red dwarf stars. These stars are smaller and cooler than the Sun, and they're the most common type of star in the galaxy. Planets in the habitable zones of red dwarfs would be in stable orbits where temperatures might allow liquid water to exist. But red dwarfs are often very magnetically active, with frequent powerful flares and intense stellar winds. The habitable zone planets, being close to their stars, will be exposed to much harsher conditions than Earth experiences. Whether these planets could actually support life depends on details of stellar atmospheric physics that Parker is helping us understand. The TRAPPIST-1 system, with its 7 Earth-sized planets, has been a particular focus of research. Several of these planets are in the habitable zone of their red dwarf host star, making them tantalizing candidates for the search for life beyond Earth. But the host star, TRAPPIST-1, is highly active, with regular flares that could potentially sterilize the planet's surfaces. Whether the planets have retained their atmospheres against the constant assault of stellar wind and radiation is a major open question. Insights from Parker's measurements of our own sun's atmosphere and wind help inform models of what's happening at TRAPPIST-1 and other systems. The search for life beyond Earth has been one of humanity's enduring quests. From the speculation of ancient philosophers about plurality of worlds to modern searches with sophisticated telescopes, the question of whether we're alone in the universe has captivated human imagination. Parker Solar Probe doesn't directly search for extraterrestrial life, but its discoveries contribute to the broader effort by helping us understand the conditions necessary for life to develop and persist. Every detail we learn about how stars work, how their atmospheres behave, how they affect their planetary systems, brings us closer to answering one of humanity's most fundamental questions. As Parker Solar Probe continues its mission through 2025 and into the years beyond, the scientific community is preparing for what comes next. The probe's primary mission was originally scheduled to end in 2025, but the spacecraft has been operating so well, and its discoveries have been so revolutionary that extensions are being planned. Each additional encounter with the sun provides more data, more chances to test theories, more opportunities to find new phenomena. The mission team is exploring how long Parker can continue operating and what science can be accomplished with each subsequent close approach. There are practical limits, of course. The spacecraft carries a finite amount of fuel for maintaining its orientation, and once that fuel is exhausted, the heat shield can no longer be kept pointed at the sun. When that happens, the spacecraft will be destroyed within a few orbits, exposed to the full intensity of solar radiation. But the team has been careful with fuel usage, and current estimates suggest Parker could continue operating into the late 2020s if conditions permit. Each additional year of operation adds to the scientific harvest. Beyond Parker itself, several new missions are being planned or developed that will build on its discoveries. NASA's IMAP mission, the Interstellar Mapping and Acceleration Probe, launched in 2025, will study the heliosphere from a different vantage point. Positioned at the L1 Lagrange point between Earth and the Sun, IMAP will measure the solar wind and energetic particles as they pass Earth's orbit, complementing Parker's observations close to the Sun. By comparing data from these different perspectives, scientists can trace how solar wind characteristics change as the wind propagates outward, providing a more complete picture of the entire heliosphere. The European Space Agency is developing a follow-up to Solar Orbiter, called the Lagrange L5 mission, which will observe the Sun from a vantage point that allows it to see solar activity approaching Earth before it reaches us. This early warning capability would significantly improve space weather forecasting, giving us hours or days of advance notice of potentially dangerous solar events. Combined with the detailed knowledge of solar processes gained from Parker, the L5 mission could transform how we prepare for space weather impacts. Looking further into the future, scientists are discussing even more ambitious missions. Some proposals involve sending multiple spacecraft to study the Sun from different angles simultaneously, creating a three-dimensional view of solar phenomena. Others involve spacecraft that would dive even closer to the Sun than Parker has gone, possibly within just a few solar radii of the surface. These missions face enormous technical challenges, but the technology developed for Parker provides a foundation that future missions can build upon. There's also discussion of missions to other stars, what's sometimes called interstellar precursor missions. These would be spacecraft sent to study the boundary region where the Sun's heliosphere meets interstellar space, and possibly continuing into true interstellar territory. The Voyager spacecraft, launched in 1977, have already crossed this boundary, but they weren't specifically designed for interstellar science. A dedicated interstellar probe could carry instruments designed to study the interaction between our Sun's environment and the broader galactic medium, providing context for understanding our place in the galaxy. These future missions all build, in one way or another, on what Parker is teaching us about plasma physics, magnetic field dynamics, and particle acceleration. The investment NASA has made in Parker is paying dividends not just through Parker's own discoveries, but through the way those discoveries enable and inform future research. This is how science progresses, in a continuous chain of investigations where each generation builds on what came before. The story of Parker Solar Probe is also a story about human persistence and ambition. The mission was conceived in the 1950s when Eugene Parker first proposed the existence of the solar wind. It took 6 decades of technological development to make the mission actually possible. Generations of engineers, scientists, and program managers contributed to bringing it from concept to reality. Some of them spent their entire careers working on the problem, retiring before the spacecraft was even launched. Others joined the project as young scientists and are now senior researchers, having dedicated their professional lives to making this mission succeed. This long timescale is typical of major space science missions. Projects like Parker can't be done in a few years. They require decades of planning, development, testing, and operation. They require institutional commitment that spans multiple administrations and budget cycles. They require continuity of expertise across generations of researchers. The fact that we can sustain such long-term projects, that we can keep teams motivated and funded across decades, is one of the great achievements of modern scientific institutions. There's also a lesson here about the value of fundamental research. Parker Solar Probe wasn't built to solve any immediate practical problem. It was built to answer questions about how the sun works, questions that had been puzzling scientists for decades. The case for the mission was made primarily on scientific grounds, the value of advancing human knowledge, not on any specific practical application that would result. Yet the practical benefits are already substantial, with implications for space, weather forecasting, climate science, exoplanet research, and our understanding of plasma physics in general. This is the way fundamental research typically works. You can't always predict in advance what practical benefits will flow from research aimed at basic understanding. But again and again, throughout history, fundamental research has paid enormous practical dividends. The development of quantum mechanics, undertaken to understand the strange behavior of matter at small scales, eventually enabled the development of lasers, computers, and modern electronics. Research on cosmic rays led to particle physics, which gave us medical imaging technology like PET scans. Studies of bacterial defense systems led to CRISPR gene editing. The list goes on. Parker Solar Probe represents a continuation of this tradition. By investing in fundamental research, by sending a spacecraft to study the sun in unprecedented detail, we're not just satisfying scientific curiosity. We're laying the groundwork for future technologies and capabilities that we can't yet imagine. Some discoveries from Parker's data will doubtless lead, decades from now, to applications that would surprise us today. The investment in basic understanding pays off in ways that are often unpredictable but consistently valuable. Of course, there are also reasons to value the research for its own sake, beyond any practical applications. The pursuit of knowledge has been one of humanity's defining characteristics throughout our history. We're curious creatures, driven to understand the world around us, to ask questions about how things work and why. The sun has been a particular object of curiosity throughout history. By understanding it better, we satisfy a deep human need to know, to comprehend, to make sense of the world. There's also something to be said about the importance of doing difficult things just because they're worth doing. Building a spacecraft that can survive inside the sun's atmosphere is an extraordinary challenge. It pushes engineering capabilities to their limits. It requires solving problems that seemed intractable just decades ago. The achievement is valuable not just for what we learn from the resulting data, but for what it demonstrates about human capability. We can do hard things. We can take on seemingly impossible challenges and find ways to overcome them. This kind of demonstration matters, especially in times when humanity faces enormous challenges that will require ambitious responses. Climate change, biodiversity loss, pandemic preparedness, all of these require humanity to take on difficult, long-term challenges. Showing that we can mobilize the resources and expertise to send a spacecraft into the sun's atmosphere reminds us that we're capable of tackling other major problems too. Parker Solar Probe is a kind of proof of concept, demonstrating that with enough commitment and creativity, even seemingly impossible goals can be achieved. Let me share some specific examples of how Parker's discoveries are already feeding into broader scientific work. Plasma physicists studying fusion energy have been particularly interested in Parker's findings about magnetic reconnection. Fusion energy, the goal of producing power by fusing light atoms together as the sun does, depends critically on controlling the behavior of hot plasma. The processes that produce switchbacks and reconnection events in the solar corona are similar to processes that occur in tokamak fusion reactors. By understanding these processes better through Parker's observations, fusion researchers can develop better strategies for controlling plasma in their reactors. The connection between solar physics and fusion energy is more than coincidental. Both involve the same underlying physics of plasmas in magnetic fields. The sun is essentially a natural fusion reactor, producing energy through nuclear fusion in its core. Reproducing this process on Earth has been one of the great goals of physics for over half a century, but it's proven enormously difficult. The challenges all relate to controlling plasma behavior in ways that allow sustained fusion reactions. Insights from Parker about how the sun controls its own plasma could inform engineering approaches to fusion reactors on Earth. Space weather forecasting is another area where Parker's discoveries are already having practical impacts. The mission has revealed that the solar wind is far more complex and structured than previously appreciated, with multiple streams of different speeds and densities interleaved with each other. This complexity affects how space weather propagates through the solar system and arrives at Earth. Updated forecasting models incorporating Parker's findings can provide more accurate predictions of when geomagnetic storms will arrive, how intense they'll be, and what impacts they'll have. Better forecasting means better protection for satellites, power grids, and other vulnerable infrastructure. The financial benefits of improved space weather forecasting are substantial. Major geomagnetic storms can damage satellites, disrupt GPS signals, interfere with radio communications, and knock out power grids over large areas. The 1989 storm that hit Quebec caused a province-wide blackout that lasted for hours and caused damage estimated in hundreds of millions of dollars. A truly major storm, comparable to the famous Carrington event of 1859, could cause damages in the trillions if it hit modern civilization. Better forecasting allows operators to take protective measures before storms arrive, reducing damage and economic losses. There's also benefit for the aviation industry, particularly for polar routes. Aircraft flying over the poles are exposed to higher levels of cosmic radiation, and this exposure can become significantly worse during solar storms. Airlines monitor space weather forecasts and may divert flights or change altitudes to reduce passenger and crew exposure to radiation. More accurate forecasts allow better decision-making, balancing operational needs against safety considerations. Parker's contributions to space weather science directly improve aviation safety and efficiency. For astronauts in orbit, the stakes are even higher. The International Space Station passes through regions of Earth's magnetic field that don't provide as much protection from solar radiation, and astronauts on spacewalks are particularly vulnerable to radiation exposure. NASA monitors space weather constantly and can have astronauts seek shelter during dangerous radiation events. As humanity expands its presence in space, with planned missions to the Moon and eventually Mars, accurate space weather forecasting becomes ever more critical for crew safety. As we move toward concluding this story of Parker Solar Probe and its remarkable discoveries, it's worth reflecting on what all of this means in the broader context of human exploration. We live in an extraordinary time. For most of human history, the sun was simply an object in the sky, beautiful and life-giving, but ultimately mysterious. Ancient peoples worshipped it as a god. Medieval scholars argued about its nature. Even relatively recent generations of scientists could only study it from afar, using telescopes and instruments based on Earth. Now we have a spacecraft actually inside the sun's atmosphere, sending back measurements from a place no human-made object has ever been before. The transformation in our relationship with our star has been remarkable. This transformation reflects a broader trend in human exploration. We're no longer just looking at the universe from a distance. We're touching it, sampling it, exploring it directly. We've sent probes to every major body in our solar system. We've collected samples from asteroids and comets. We're planning to bring back samples from Mars. The exploration of space is moving from observation to engagement, from distant viewing to active investigation. Parker Solar Probe is part of this broader transformation, perhaps its most dramatic example. Sending a spacecraft into the sun's atmosphere is the equivalent of putting a thermometer inside a furnace. It's a level of direct investigation that previous generations couldn't have imagined. And yet, here we are, accumulating data from inside our star, learning its secrets in ways our ancestors could only dream of. What's particularly striking about Parker's discoveries is how they connect to broader questions about complexity in nature. We've talked about magnetic reconnection, switchbacks, multi-temperature plasmas, self-organization, and a host of other phenomena. What unifies all of these observations is the realization that the corona is far more complex than we had imagined. It's not just a hot atmosphere. It's a richly structured, dynamically evolving system with multiple interacting processes, operating across many different scales. This kind of complexity is showing up everywhere we look in nature, not just in the sun's corona. As measurement tools improve and observation techniques become more sophisticated, scientists are finding that natural systems are typically far more complex than simple models suggest. Biology, neuroscience, climate science, ecology, all of these fields are encountering similar lessons. The simple models we develop to understand systems are useful but incomplete. Real systems have layers of complexity that emerge from interactions among many components, and capturing this complexity requires new approaches. Some researchers see in this trend the outlines of what might be called a new physics of complex systems. Rather than trying to reduce everything to simple fundamental laws, this approach focuses on understanding how complexity emerges and how it can be characterized mathematically. The work on self-organization, on critical phenomena, on emergent behavior in many body systems is laying the groundwork for this new approach. Parker's discoveries about the solar corona fit naturally into this framework, providing detailed data on a complex system that can inform broader theoretical development. The implications for how we understand the universe are profound. If complexity is the rule rather than the exception, if natural systems typically involve emergent behaviors that can't be predicted from their components alone, then much of our scientific understanding needs to incorporate this perspective. We need theories that can handle complexity, that can predict emergent behavior, that can deal with systems where the whole is genuinely more than the sum of its parts. Parker's contributions to solar physics are also contributions to this broader scientific transformation. There's a humbling aspect to all this. The Sun has been the most studied star in the universe, an object close enough to be observed in detail using countless instruments over centuries. And yet, when we finally got close enough to make in situ measurements, we found surprises everywhere. Every measurement seemed to reveal new mysteries. Every solved problem opened up new questions. This pattern suggests that we should expect similar surprises wherever we look closely enough in the universe. Other stars, other galaxies, other phenomena all probably have layers of complexity we haven't yet appreciated. We have much more to discover than we realized. This humility about the limits of our knowledge is healthy for science. It guards against the kind of overconfidence that can lead to dogmatic thinking and missed discoveries. The history of science is full of examples where scientists were too certain about their understanding, only to be proven wrong by later evidence. Parker reminds us to stay open to new possibilities, to expect surprises, to be willing to revise our theories when observations demand it. At the same time, there's reason for optimism about how science can address these challenges. Despite the unexpected complexity Parker has revealed, scientists are making real progress in understanding it. New theoretical frameworks are being developed. Better models are being constructed. Cross-disciplinary collaborations are bringing fresh perspectives to old problems. The scientific community has shown itself capable of grappling with the corona's complexity, even as that complexity continues to surprise us. This progress isn't just academic. The understanding we're developing has real-world applications, as we've discussed. Better space weather forecasting, improved climate models, more accurate assessment of exoplanet habitability, potential applications in fusion energy and other technologies. All of these benefit from Parker's contributions. The investment in fundamental research is yielding practical returns, even as it answers questions that have puzzled humans for centuries. Let me share one final aspect of Parker's discoveries that I find particularly fascinating. Throughout the mission, scientists have been struck by how the data sometimes seems to defy not just specific predictions, but broader expectations about how physical systems should behave. There are moments when the measurements suggest the corona is doing something genuinely new, something that fits no existing framework. These moments are rare and require careful verification, but they exist. They suggest the possibility that we might be on the verge of discovering genuinely new physics, phenomena that require fundamental advances in theory to understand. This is the kind of opportunity that makes scientists' hearts race. The chance to discover something truly new, not just a refinement of existing understanding, but a genuine expansion of our knowledge of how nature works. Whether Parker's data will ultimately lead to such fundamental discoveries remains to be seen. The history of science suggests caution about claims of revolutionary new physics. Many apparent anomalies eventually turn out to be explainable within existing frameworks, perhaps requiring some refinement, but not requiring fundamentally new theories. But the possibility exists, and it adds to the excitement around the mission. Whatever the final scientific assessment, Parker Solar Probe will be remembered as one of the most important space missions of the 21st century. The data it has collected will be studied for decades. The phenomena it has discovered will inform models of stellar atmospheres throughout the universe. The engineering it has demonstrated will enable future missions to extreme environments. The legacy of Parker is just beginning, even as the mission itself continues. There's something poetic about the timing of all this. We're learning about the sun in unprecedented detail, just as humanity is becoming increasingly dependent on technologies vulnerable to solar activity. The infrastructure of modern civilization, electrical grids, satellite networks, GPS systems, internet communications, all of these can be disrupted by space weather. As we become more dependent on these technologies, we become more vulnerable to solar storms. Better understanding of the sun, enabled by Parker, comes at exactly the time when that understanding is most needed. This convergence of scientific discovery and practical necessity isn't accidental. Throughout history, fundamental research has often advanced in step with practical needs, as if guided by some invisible hand. Sometimes the connection is direct, with research aimed at solving specific problems. More often, the connection is indirect, with research pursued for its own sake, yielding practical benefits in unexpected ways. Parker Solar Probe fits this pattern. The mission was designed primarily to advance our scientific understanding of the sun, but its results are also helping us protect critical infrastructure and prepare for space weather impacts. The story of Parker also illustrates how science is fundamentally a collective endeavor. While individual scientists and engineers have made crucial contributions, the success of the mission depends on the combined efforts of thousands of people across many institutions and countries. From the original concept, developed by Eugene Parker in 1958, through decades of theoretical and observational work that motivated the mission, through the engineering challenges of building the spacecraft, through the operations team that manages it daily, through the scientists worldwide who analyze its data, the mission represents an enormous collective achievement. This collective nature of science is sometimes obscured in popular accounts that focus on individual heroes. Eugene Parker is rightly celebrated as the scientist whose ideas inspired the mission, but he was one of thousands of people whose work made it possible. The story is more accurately told as one of community, of people working together across generations to address a common challenge. This story has its own kind of beauty, perhaps more meaningful than the lone hero narratives that dominate popular imagination. It's a model worth remembering as humanity faces other challenges. Climate change, pandemic preparedness, biodiversity loss, all of these require collective action across generations. The example of Parker Solar Probe shows what's possible when humans coordinate their efforts toward long-term goals. We can sustain commitments across decades. We can build institutions that outlast individual careers. We can pass knowledge from one generation to the next, building cumulative understanding. These capabilities will be essential as we tackle the major challenges of the coming century. There's also a message of hope in Parker's story. In a world that often seems divided and dysfunctional, the success of a mission like Parker demonstrates what humanity can accomplish when we focus our efforts on positive goals. The mission required international cooperation, sustained funding, technical excellence, and shared commitment to a common purpose. The fact that we can still do these things, that we can still mount ambitious projects that succeed against tremendous odds, is genuinely inspiring. It suggests that we're capable of more than our current political and social divisions might suggest. As Parker continues its mission, more discoveries lie ahead. Each close approach to the sun brings new opportunities for surprise. Each year of operation extends the temporal coverage of our observations, allowing us to track how solar phenomena vary over time. Each new analysis of the accumulated data has the potential to reveal patterns and connections that weren't visible before. The mission isn't just adding to our knowledge incrementally, it's transforming our understanding in ways that will continue to unfold for years to come. So where does the Parker Solar Probe mission leave us as we conclude this exploration of its remarkable achievements? We stand at a unique moment in human history, having accomplished something that would have seemed impossible just a few generations ago. We've sent a spacecraft into the atmosphere of the Sun. We've retrieved data from inside the corona, from a region so hot and so violent that all our intuitions about what's possible needed to be revised. And what we've found has revolutionized our understanding of not just our star, but of stellar physics in general, of plasma behavior, of the connections between magnetic fields and matter throughout the universe. The discoveries we've discussed throughout this story represent only a fraction of what Parker has revealed. The magnetic switchbacks that turned out to be ubiquitous near the Sun. The patchy temperature structures that defy traditional models. The bidirectional plasma flows that complicate our picture of the solar wind. The energetic particles being accelerated by mechanisms we're only beginning to understand. The complex radio emissions that hint at new wave phenomena. The persistent density structures that suggest self-organization in the corona. The detailed characterization of multiple solar wind streams with different origins. The connections to fundamental questions about how complex systems behave throughout nature. Each of these findings represents years or decades of work to fully understand. Each opens new research directions. Each contributes to a transformed view of how stars work. But beyond the specific discoveries, there's something more profound to consider. Parker Solar Probe has shown us that even objects we've studied for centuries can still surprise us. The Sun has been observed continuously by various instruments for many decades, by scientists professionally for centuries, by humans informally throughout our history. And yet, when we finally got close enough to make in situ measurements, we found mysteries everywhere. Every measurement revealed new questions. Every solved problem opened up new puzzles. This pattern carries a profound lesson about the nature of scientific knowledge. We're never really finished understanding anything. The universe is deeper, richer, and more complex than our current theories suggest. There's always more to discover, more nuances to appreciate, more connections to uncover. This isn't a discouraging thought. It's an exhilarating one. It means there's no end to the journey of discovery. There will always be more to learn, more to explore, more to understand. For young people considering careers in science, this is perhaps the most important message of Parker's story. The questions aren't all answered. The discoveries aren't all made. The Sun, our nearest stellar neighbor, is still surprising us after centuries of study. If our most familiar star can still teach us so much, imagine what other stars might reveal. Imagine what we might learn from galaxies, from the intergalactic medium, from the early universe, from exotic objects like black holes and neutron stars. The opportunities for discovery in our generation and the next are essentially limitless. The Parker mission also illustrates the importance of patience in scientific endeavors. The mission was conceived in the 1950s. The technology to make it possible took decades to develop. The spacecraft itself took years to build and test. The mission has been operating since 2018, with discoveries continuing to emerge year after year. From concept to current state, we're looking at roughly 7 decades of sustained effort, with the full impact of the mission still being realized. This timescale is humbling. It reminds us that some of the most important work requires patience and persistence across generations. The contrast with our current cultural expectations of instant results is striking. We live in an era of social media, where attention spans are short, where everyone wants immediate gratification, where complex problems are expected to have quick solutions. Parker's story reminds us that some things are worth waiting for, worth investing in over the long term, worth building toward across generations. This perspective matters not just for science, but for many aspects of human endeavor. The challenges humanity faces, from climate change to economic inequality to social cohesion, all require sustained effort across many years. The example of Parker shows that such sustained effort is possible, that we can mobilize resources and expertise over decades to address complex problems. Of course, mention should be made of the international dimension of all this work. While NASA leads the Parker mission, scientists from around the world contribute to analyzing the data and developing theoretical frameworks to interpret it. The findings are published in journals read globally. The discoveries enter the broader scientific record that humanity shares. This international cooperation in science is one of the genuinely positive aspects of our current era. Despite all the political tensions and conflicts that divide nations, science continues as a fundamentally collaborative enterprise. Researchers in countries that are politically at odds nonetheless cooperate on scientific problems, share data, and build on each other's work. This collaboration represents one of the better aspects of human nature, a recognition that knowledge transcends national boundaries and that we're all part of the same intellectual community. Looking ahead, the future of solar physics looks bright. New missions are being planned. New telescopes are coming online. New theoretical approaches are being developed. The next few decades will likely see even more revolutionary discoveries about the sun and stars in general. We might finally definitively solve the coronal heating problem. We might understand exactly how the solar wind is accelerated. We might predict solar flares and coronal mass ejections days or weeks in advance. We might map the connections between solar interior dynamics and atmospheric phenomena in detail. We might discover entirely new phenomena that we can't even imagine today. Beyond the sun, the same questions and methods can be applied to other stars. Future telescopes will image the surfaces and even atmospheres of nearby stars in detail. We might detect stellar coronas of nearby stars and characterize their properties. We might study how different types of stars handle the same fundamental physical processes that Parker has revealed at the Sun. The Sun is our laboratory for understanding stellar physics in general, and the lessons learned will apply to stars throughout the universe. There's also the longer-term prospect of actually visiting other stars. Currently, this seems like distant science fiction, with the technology required vastly beyond what we can build. But projects like Breakthrough Starshot, which proposes sending tiny laser-propelled spacecraft to Alpha Centauri at significant fractions of the speed of light, are showing that interstellar travel might be possible within a century. If we eventually send probes to other star systems, the knowledge we're gaining about how stars work at our own sun will be essential to interpreting what we find when we get there. Parker is laying groundwork for explorations that might happen long after the current generation of researchers has passed on. Some readers might wonder whether all this effort is worth it. The Parker mission cost billions of dollars. The follow-on missions will cost more. The total investment in solar physics over the past few decades represents enormous resources that could have been spent elsewhere. Is this really the best use of humanity's wealth and effort? The answer involves several considerations. First, the practical benefits of solar physics research, particularly for space weather forecasting, are substantial and growing. As our civilization becomes more dependent on space-based and electrical technology, accurate understanding of solar activity becomes more economically valuable. The cost of major space weather events, when they occur, can far exceed the cost of all the research that helps us understand and predict them. Second, the technological developments required for missions like Parker have applications far beyond their immediate purposes. The heat-resistant materials developed for the spacecraft's thermal protection system have applications in other extreme environments. The autonomous navigation systems have applications in many fields. The data analysis techniques developed to extract science from Parker's measurements apply to many other types of complex data. Investment in challenging space missions tends to generate technological spin-offs that benefit broader society. Third, the scientific knowledge itself has value. Understanding how the universe works is one of the great achievements of human civilization. We're not just here to consume resources and reproduce. We're a species capable of asking fundamental questions about reality and pursuing answers to those questions. Solar physics is part of that broader pursuit of understanding. The knowledge we gain enriches human civilization in ways that go beyond practical applications. Finally, there's the question of inspiration. Missions like Parker excite people about science. They motivate young people to study physics, engineering, mathematics. They demonstrate what humans can accomplish when we focus our efforts on ambitious goals. The inspirational value of such missions is hard to quantify but real. They contribute to a culture that values knowledge and exploration, qualities that benefit society in countless ways. So yes, the investment is worth it. The combination of practical benefits, technological spin-offs, scientific knowledge, and inspirational value makes missions like Parker Solar Probe excellent investments. We should be doing more of them, not fewer. As we close this story, I want to leave you with a final thought. Parker Solar Probe is currently somewhere in our solar system, continuing its journey around the Sun, accumulating more data, preparing for more close encounters. Right now, as you're reading this, the spacecraft is doing its work, slowly but steadily revealing the secrets of our star. It's a tangible representation of human curiosity and capability, a small machine carrying instruments built by human hands and minds, traveling through space at speeds that would have seemed impossible to our grandparents, doing science that will benefit generations not yet born. The sun has been with us throughout human history. It will continue to be with us for billions of years to come. But our relationship with it is changing. We're moving from awe and worship to understanding and partnership. We're learning to live with our star, to predict its behavior, to harness its energy through solar power, to anticipate its dangers. This evolving relationship with the sun is part of humanity's larger maturation as a species, our growing recognition of our place in the cosmos. What Parker Solar Probe saw after touching the sun is changing physics, yes, but more importantly, it's changing how we see ourselves and our place in the universe. We're a species capable of building a spacecraft that can survive inside a star. We're a species capable of asking deep questions about how the universe works and finding answers to those questions. We're a species capable of sustaining long-term scientific endeavors across generations, building cumulative knowledge that benefits all of humanity. These capabilities deserve celebration. They give us reason for hope about what we might accomplish in the future. Thank you for joining me on this journey through one of the most remarkable scientific adventures of our time. The story of Parker Solar Probe is still being written, with new chapters added every year as the mission continues. Whether the discoveries we've discussed lead to revolutionary new physics or refinements of existing theories, the mission has already changed how we understand our star. And in the process, it has reminded us of something important about ourselves, that we're curious creatures capable of extraordinary achievements when we put our minds to it. Keep looking up at the sun, though never directly without proper protection. Think about Parker Solar Probe out there, diving into its atmosphere, sending back data that's transforming our understanding. Wonder about what other mysteries are still waiting to be solved, about other questions still waiting to be asked. The universe is vast and complex, full of surprises, and we're privileged to live in a time when we can explore it in unprecedented ways. Good night, and keep your curiosity alive, because there's so much more out there waiting to be discovered.